Hello everyone, welcome back to the channel. Today we are going to be addressing a very cool problem, and in the solution we are going to see a very nice data structure to solve that problem. So without wasting any further time, let's dive right into the video. So the agenda for this particular video is we are going to start by talking about the social network problem that we have, and then we are going to discuss about a few different approaches to solve that problem. Then we're going to jump on and talk about union find, the data structure that optimally solves this problem. And then we're going to talk about algorithm for implementing union find, and last but definitely not the least, we're going to talk about the code for this problem. So let's jump into discussing the problem statement. So the problem statement for the problem is, given n connections in a social network where connections can be added at any time, answer queries of the form a hyphen b, which tells if a given person A is connected to B or not. So let's say we have to output yes or no, right? So let's just quickly discuss an example to understand this better. So let's say we have person A, person B, person C, person D, and person E in a social network, right? And I say that at any point I connect A and B, let's say, right? So I make A and B connected, I make C and D connected, and I now ask you the queries like A to B, A to C, E to D, right? If you take a look closely, then you see that A and B are connected. So we say that, yeah, the answer is yes. A and C are not connected, so the answer is false. E and D are not connected, the answer is false. Now let's say another join type of query happens and we make this connection, B to C, right? So what will be the answer in case of A to C? It should be true, right? Because the connection is established. Well, now obviously when you see this problem, you encounter that, okay, this is a graph problem, right? Best way to model a social network is using graphs, right? So one approach to solve this problem is by maintaining an adjacency list and then traversing that adjacency list using DFS. So let's say we have connections like the example we discussed. So we have A to B and we have C to D, right? So in this case, adjacency list, and let's say we have E as well. So adjacency list will look something like A will have B in its adjacency list, C will have D in its adjacency list, B will have A in its adjacency list. Since it's mutual, right? Mutual friendship, so it'll be unidirectional. It'll be undirected. So we have A to B, C to D, B to A, and we'll have D to C as well. And E will have an empty list. It's not connected to anything. And then when you are asked, let's say that B and D are joined now. So in that case, what you do in B's adjacency list, you add D as well, and in D's list you add B. So in D's list we add B. Right. So now whenever we have to handle a query, so basically now join operation is like a constant time operation, but every time when we have to check if given two nodes are connected or not, we have to start a DFS from the starting node. So let's say we have to check if A and C are connected or not, right? So start a DFS from here, we go to B, we go to D, and then we reach C, right? And similarly, if we have to check if B and C are connected or not, we have to start a DFS from B, go to D, and then go back to C, and we go to C and then check, okay, yeah, so these two are connected, so I can say that they are connected and they are friends of each other, right? So every query, I mean, in worst case, it could go toward the length of the entire chain, right? So it would be O of n per query, right? So that's not good enough because join is constant time is fine, but we have to like again and again DFS for every query. I mean, we are not, so if someone says like A and C are connected while traversing from A to C, we are seeing that B and C are also connected, but we are not storing that kind of information. That's going waste, right? So that's a total waste of time, and again giving O of n time per query. Now let's talk about union find and how to solve this problem efficiently using union find. Alright, so union find, as the name suggests, right, this data structure supports two kinds of operations, union and find. And what are these X and Y? These are sets basically. So let's talk about our problem and model it in terms of union find, right? So let's say we have 5 people, A, B, C, D, E, and E initially. Let's say both of them are all of them are parents of each other, which means that they belong in disjoint sets, right? None of them have common parent, right? So let's say we do a union of A and B. So when I say that I do a union of A and B, I mean to say that A and B are friends of each other. So what we do is we make B is parent A, or we make A as the parent of B, right? So something like this starts happening, right? and then I say that, okay, now let's connect A and C. So in that case, I make C's parent as A. Okay. And then I say that, okay, now let's say that C and E are connected. So I'll make E's parent as C. E's parent will become C. And now D is again, D is its own parent, right? So now again, let's try to see what this find function does and how do we solve our problem. So let's say I want to check if E is connected to A or not, right? So now the problem becomes finding if E has A as its parent or not, right? Or E and A both have same parent or not, right? So what is the parent of A here in this case? A has A only as parent. So find of A returns A, right? Now find of E. So what happens? So I check parent of E, which is C. And C is C's parent C? No, right? So we again come up, we come to A. And we stop when we find a node where the parent of that node is the node itself, right? So at A, the node of the parent of A is A itself. So we terminate our search and we return that find of E is also equal to A. And since both the find operations returned us the same value, then we can say that, these two things are connected, right? Quickly take an example of something which is not connected. So D. So parent of D is D itself. So find of D would return D, right? And find of, let's say, B. Find of B would return A. Same way, going recursively up the tree. A and D not equal to same, so these are not connected, right? Now you'd say that again, you'd argue, see, again, we are, spending linear time per query because this chain can be linearly longer, right? And where n is the number of elements or the number of people we have on a social network. So there are a few optimizations which we'll talk about when we are implementing the solution and in the next section as well. So this is the basic idea of implementing this problem using union find data structure. We have these two functionalities supported by the data structure, union of two sets and find. While making union, we just put one node's parent as another, and while find, we just recursively go up while we don't find a node which is the parent of itself, right? So this is the simple algorithm to model our problem using union find. In the next section, let's talk about implementation and about the optimizations, how to reduce this time to almost a constant time. As we observed during our last example, the time complexity for find operation was still linear, right? So let's talk about the optimizations. So there is this cool optimization called path compression, which basically reduces the chain that we have to travel while using find query. So let's say we are searching for the parent of E. Now while going up, we travel from E to D, D to C, and C to A. Now obviously A is the parent of C, A is the parent of D, A is the parent of E, right? So in that case, while path compression, what do we mean is to compress this path. So what we do is, so while we are recursively traveling up the tree, we make all of them the direct children of the given parent, right? So after path compression, this would look something like this: A to B, C, D, and E, right? So now if you see, this problem is just like one step, so you just going one step ahead. So with path compression, the length of your tree will never exceed more than 1 with path compression. Then another thing that we have optimization while in case of union of these two sets is union by size. So what I mean by that is, let's say we have two things, A, B, C, D, and E, right? So let's say I make D and E as friends of each other, right? So if D and E are made friends of each other, so I think by our simple definition of union, we would make D's child as E, or we would make E's child as D, right? This is the approach. And then again, with D, we have multiple links available, right? So well, union by size, what you do is you always try to make the parent as the one which has less size, which has less number of nodes. So this size array is something that we'll maintain separately, which we'll see while implementing the code. Now let's talk about the code for solving this problem. So as you can see, the code is in Java, and I have this public class DSU, and inside this I have a static class which is private, and the name of the class is union find. So here is the class which has the implementation for our two basic functions, which is union and find, as you can see, right? So let's just go line by line and just dry run and understand what this class does. the first variable we have is capacity, which stores the size of the number of elements that we are going to store in our union find data structure. Second is the parent array, as we discussed in the previous examples, right? We need something to store parents, and all the values here are going to be integers. And then we have something to store the size of the trees as well, so that while doing union, we can, efficiently join the two trees based on which size is lesser. So I've just left a comment that, for union by rank, this is being used. The constructor, it takes an integer n number of elements, sets this to capacity. I'm initializing parent array, size array, and initially the size of all the subtrees are 1 because every node is a parent of itself, right? And that's what I'm doing here as well. Parent of I is I. Next thing, let's check about the implementation of find function. So it takes a given value and returns which set it belongs to, right? So while the search ends when we reach a node which is the parent of itself, right? So while x not equal to parent of x, let's go to line number 25, x is equal to parent of x. So we keep on traversing up in the tree. This line number 24, if you see carefully, parent of x is equal to parent of x. This is what is path compression, right? So while we are traversing up, we make this parent as the parent of parent, right? So basically we are reducing the size of the branch, size of the tree. And that's why it's called path compression. Now, even if I remove this, it will work perfectly, but then the time complexity increases. Now let's talk about union. So union, basically what it does is it calls, it takes two elements, x and y, checks, finds out in which sets these two elements belong. So set x, set y. So if they already don't belong in the same set, then we check for the sizes, and this is just, these three lines are just swapping these two variables. So what I want is, I always want to have these two things, size of set x. I'm always assuming that the set x is smaller than set y. So that's why I have to implement a swap whenever the size of set x is greater than set y. And then we just set the parent, and then the function rFriends takes two elements and just returns if they both belong to the same set. If they belong to the same set, then they are friends of each other, right? And getSize just returns the number of elements that our DSU data structure holds. So let's go through an example. So we have instantiated union find class with n equal to 100 elements. We are making 1 and 2 as their friends. 2 and 4 are friends. 1 and 3 are friends. So 7 and 5 are friends. 5 and 6 are friends. And then we are checking if 1 and 2 are friends. So it should return true, right? 1 and 2 are directly connected. If 1 and 4 are friends, so 1 is connected to 2, 2 is connected to 4. So they are indirectly connected, but are essentially friends of each other, right? So by the definition of the problem, so we have 1 and 4 are connected, so this should also return true. Now we go about 1 and 6. So we can see in this example 1 and 4 are connected, 1, 2, 3, 4 are connected, 5, 6 and 7 are connected, so 1 and 6 are not connected. So this should return false, right? So let's quickly run this and see what it returns. So yeah, so it returns true and false. If you want to see another example, let's just quickly say, let's say 1 and 7 should return false because we don't have a direct connection. Now let's make a connection between them, right? So that's what the problem is, right? Dynamically we have to make joins between two elements. So union find union 1 and 7. Let's do a union of 1 and 7, right? And then again run this, and this should return true now. So true, true, false, true, right? So that's how we implement DSU using simple parent array and size array, and we have implemented path compression and union by size, right? So, well, if you guys enjoyed watching this video, then make sure to give this video a thumbs up and also subscribe to the channel if you haven't already, because we're gonna keep coming with these amazing videos. If you have any doubts or you have any other questions, feel free to drop them down in the comment section. And until next video, take care. Bye bye.